Yeah. Okay, so can you see the PowerPoint slides that I'm sharing, and can you hear me? Yep, good. All right. Thanks for the thumbs up. Okay. Right. Okay, so yeah, I hope you're having a good week. And this is lecture 7 of 124 103 Biophysical Principles. We Yeah, in this lecture, we'll still continue talking about the laws of motion. So last time, we already started talking about why the objects move. So in the beginning of this course, we were describing the object's motion, and now we've moved on to talking about why the object is moving in the first place. And last time we already learned that it's because force is being exerted on the objects. That's why they are moving. And we learned about forces, how to draw the forces that are acting on the object, and then we started to look at the Newton's laws of motion. So in this lecture, we'll just continue on looking at Newton's laws of motion and force. How do we get the net force acting on the object? Yeah. So last time we said Newton's laws of motion. There are 3 of them, and they describe the connection between the forces that act on an object and the object's movement, right? And last time we talked about Newton's first law of motion, which says that if the net force along the horizontal is 0, and the net, when we say net, it's total. So when the total force along the horizontal is 0 and the total force along the vertical is 0, meaning the total net force overall is 0, then the object will just keep doing what it's doing. If it's initially at rest, then it will stay at rest. And if it's initially moving, it will keep moving with the same speed and in the same direction. Right? So that was first law of motion. And we look at some examples of when the net force is 0, the object will remain at rest, or it will move with constant velocity, meaning 0 acceleration. So the second law of motion, Newton's second law of motion, says that the acceleration of an object is directly proportional to the net force and inversely proportional to the object's mass. So the second law of motion now gives us the direct relationship between the acceleration of the object and the net force that's acting. Right? So what do we mean by directly proportional and inversely proportional? So if you think about it, the relationship between acceleration and force logically, it's sort of quite intuitive, because, for example, you have an object with a certain mass m, and you apply a very large force. So say you have a small ball and you push it really hard. Will the ball move fast, or will the ball move slowly? If you're putting like a big force, if you're pushing it so hard and the mass is quite small, yeah, it will move fast, right? Because you pushed it really hard. So you will have a big acceleration if you're pushing something really hard, right? Compared to when you have the same mass, the same object, but you're pushing it with just a small force, yeah, just a weak push, right? Then it will make sense that the object will move slowly. So you have a small acceleration, right? On the other hand, so this is what we mean by direct proportionality. Yeah, if you apply a big force, you get a big acceleration. If you apply a small force, you get small acceleration. Yeah. What do we mean by inverse proportionality? This inversely proportional. So that's with respect to mass. So that means if you have a big mass, a very heavy object, and you're applying, say, some force on that object and it's very heavy, will you get a large acceleration or a small acceleration if you're pushing a very heavy thing? Do you think you'll get a small acceleration or a big acceleration? Yeah, small, right? So you can imagine pushing a car as opposed to pushing a chair, for example. The car is so massive, you'll get a small acceleration for that, as opposed to when you're pushing a small mass with the same amount of force, okay, then you'll get a big acceleration. So inverse proportionality means something small results to something big, and something big results to something small. So big mass results to small acceleration, small mass results to big acceleration. Yeah, and so then you have this equation that the acceleration is directly proportional to the net force and inversely proportional to the mass. Yeah, that's Newton's second law of motion. Don't forget that acceleration and force, they're both vector quantities, meaning direction is important. And mass is a scalar, so mass doesn't have a direction. That means the direction of acceleration is influenced by the direction of the force. Okay? So the direction of acceleration will be equal to the direction, or it's the same as the direction of the net force. All right. Okay, I hope that makes sense, so that it's not just an equation that you're looking at, but it actually has some physical meaning behind this equation for Newton's second law of motion. Right. So if we rearrange Newton's second law of motion so that we isolate F net, and yeah, let's do a little bit of revision. So if you're starting from this starting equation for Newton's second law of motion and you want to isolate net force, the method we learned before, you sort of build up the equation starting from what you want to isolate, F net. You divide that by the mass. Okay. Then you get F net divided by the mass, which is equal to acceleration. Then you sort of go back, retrace your steps backwards, starting from acceleration, and you undo whatever you did to build the equation up. So instead of dividing, you multiply with m. Then you have mass times acceleration, and you end up with net force. And therefore, net force is equal to mass times acceleration, right? But yeah, we'll be seeing a lot of these three variable equations, and we will be rearranging some of them quite a bit. So so you can go this route, the one we learned how to rearrange, or later, as you do this method, you will soon find out that there's actually a pattern. That if you have just three equations, you can use the mathematical identity rule that says anything divided by itself is equal to 1. So you can just go F net is equal to mass. Let's start from the starting equation. Yeah, that's acceleration is equal to F net divided by mass. Okay, if you wanted to isolate F net, there's a mass in the denominator of the equation here. If you apply the rule that any number, yeah, I'll get to the question in a bit. So if you apply the mathematical rule that any number divided by itself is equal to 1, you can multiply both sides with the mass m, so that m divided by m is equal to 1, right? And you're just left with F net on the right side, and whatever you do on the right side, you do on the left side. So if you multiply the right side with m, you have to multiply the right side with m as well, and you also get F net equals mass times acceleration. So you can do both ways of rearranging. So there's a question here. Do you need to worry about air resistance with this law? So air resistance is a kind of friction. right? Friction, of course, will affect the motion of the object. So yes, if the problem states explicitly that there is air resistance, then you have to worry about air resistance. But where will air resistance come into this equation? It will come into F net. So F net is the combination of all the forces acting on the object. So when you calculate the F net, that's where you include air resistance. Right? Does that answer your question, Liza? Does it make sense? Yep. Okay, good. Cool. Right. So yeah, so this is the more commonly seen form of Newton's second law of motion, F net equals mass times acceleration, which is probably more intuitive if you think about it. If you're applying a force on an object, it will accelerate, or it means that if the object is accelerating, it means that there's a net force acting on it. All right, so let's look at some examples of Newton's second law of motion. You have here two scenarios. So you have a kind of tug of war here. A girl who weighs 30 kilograms is being pulled by two people at opposite ends. What will be the acceleration of the girl in the first case here, in the first scenario, where you have 5 newtons of pull to the right and 5 newtons of pull to the left? What will be the acceleration of the girl in this first scenario here? Yeah, good. Yeah, I can see there 0. Very good. Why is it 0? Newton's second law of motion says net force is equal to mass times acceleration, or acceleration is net force over mass. Okay, so first you need to figure out what is the net force. Net force is now adding up all the forces. Considering all the forces, you have two forces, 5 newtons. They're both 5 newtons, but they're at opposite directions. We learned last time that if the forces are acting along the horizontal in the same axis, but at different directions, you subtract them, and so the net force is 0. That will result to 0 acceleration. How about for the second case? What's the acceleration of the girl in the second case? Right. So again, you have to you have to figure out what's the net force, because it's the net force, it's the total force acting on the object that will influence the acceleration. Yeah. And yeah, I can see there 0.1 is the correct answer. So you have 8 newtons to the right and 5 newtons to the left. That means they're in opposite directions. That means you subtract those two forces as well. Okay, so the net force is 3 newtons, and then you divide that by the mass, okay? Because acceleration equals net force divided by the mass, and you have 0.1 meters per second squared. In which direction will the acceleration be? Which way will the girl move? Towards the boy, or towards the man, or towards the woman? Yeah, good. Yeah, it will be towards where the bigger force is. Yeah, whoever is pulling harder, that's where the girl will move towards. So it will be to the man to the right. Okay, right. So let's look at another like worded problem type. A car pulls a 500-kilogram trailer along a rough road, and the car and the road supply a net force of 1,000 newtons. Calculate the acceleration of the trailer. Yeah. So I'll let you think about that for a minute, and I'll just answer the question there. How do you convert newtons per kilograms to meters per second squared? So it's not the conversion. So so newtons, you're right. The unit for force, I need some more. Unit of force is the newtons. Newtons is a special name for kilogram times meter divided by second squared. And so when you have the net force divided by mass, net force is kilograms. So we'll do here, the equation for acceleration is net force per meter divided by mass. So the unit for net force is kilograms meters per second squared, which is the expanded meaning for newtons. And then you divide that this by kilograms, which is the unit of mass. So that's where the kilograms will cancel each other out, and you're left with meters per second squared. So yeah, so I think as long as your mass is in kilograms and your net force is in newtons, then automatically the acceleration will be in meters per second squared, and you don't have to worry about doing this expanding newtons and doing this calculation for the unit of acceleration. So just make sure your mass is in kilograms and your net force is in newtons. That will automatically give you a unit for acceleration of meters per second squared. Cool. Right. Okay, so let's go to this problem. You have a net force of 1,000 newtons. So net force is given. That means, yeah, so you know it's a rough road. So you know there's some frictional force in the opposite direction of the movement. And then you have this pulling force. Let's just say it's an applied force. It can be tension force if you consider it through this connection, but let's just call it applied force. But the problem already gives you net force. That means it has already calculated for you the effect of friction and applied force, and to include the question earlier about air resistance, it's also included there in the net force. So all the forces acting on the trailer has already been included in this 1,000 Newton force, right? And so you just have to calculate now for the acceleration of the trailer. Right? And Newton's second law of motion gives you this equation that you can use to directly relate the net force and the acceleration. You can again have to rearrange this equation to get the equation for acceleration. I'll just do the shorter way. Dividing a number by itself is equal to 1. So if I divide both sides by the mass, because I want to isolate acceleration, if I divide both sides with the mass, I see here mass divided by mass, that's equal to 1. So the right-hand side will just be acceleration, and the left-hand side will give me net force divided by mass. Okay. And I'll just substitute the numbers, giving you an acceleration of 2 meters per second. For the size or magnitude, the direction will of course be towards the direction of the pulling force. Okay. All right. Are we is that any problems or any questions about the solution? Yep. Okay, good. Thanks for the thumbs up. All right. So net force really does determine the object's acceleration, and that's why we always want to determine the net force. It's not the individual forces, but it's the combined effect of all the forces acting on the object. Yeah, net force being the combination of all the forces. And last time we learned that, and we've been seeing this, that if the forces are just along the horizontal, along a straight line in the horizontal or vertical, it's easy to get the net force, because if they're in opposite directions, you just subtract the forces. If they're in the same direction, then you just add the forces. So it's easy to get the net force if they're just along the horizontal or all the forces are along the vertical. If the forces are diagonal, making an angle with respect to the horizontal or vertical, then that's a little bit more complicated. And you have to sort of manipulate that diagonal force in order to get the horizontal and vertical. And last time we started looking at the diagonal force and we learned how to get the net force using the parallelogram method, just drawing the forces. And so you sort of have to copy one force onto the other. Yeah, copying F1, connecting that to F2. Notice how the tail of F1 connects with the head of F2, and then you copy F2 as well, connecting. Notice how the tail of F2 is connected with the head of F1, and then the net force. Yeah, my drawing's not so good here, so just look at this drawing here, but connecting the tails of all the forces with the heads of all the forces will give you the net force. And we learned this method last time of finding the net force, but it's a little bit tedious. You have to measure the exact lengths of your forces to get the exact size of your net force. Okay, so today we will learn another method of finding the net force, and it's a little bit mathematical, but we'll go through it slowly. And as we're going along and it's getting confusing, just feel free to pop a comment on the chat box or ask a question if it gets a little bit too maths difficult, if you want to put it that way. Right, but the other method is called component method, finding the net force. And it's called component method because every diagonal force will have a horizontal and a vertical component. And in this method, we will try to get the horizontal component and the vertical component of the diagonal force. Why? The horizontal, we want to go to the horizontal and vertical conditions because we know it's easy to add forces when they're all horizontal or when they're all vertical. So the horizontal component, we also call that X component because it's along the X axis. And the vertical component, we also call that Y component because it's along the Y axis. The really important thing to note here is that the vertical and horizontal components, they are perpendicular to each other. Okay? Perpendicular means that there's an angle of 90 degrees between them, and they're like perpendicular. Since they are perpendicular to each other, the components, the horizontal component, the vertical component, and the diagonal force form this right-angled triangle. Okay? And it's because of this right-angled triangle that that we will be able to apply trigonometry to calculate the vertical and horizontal components, and we'll get through that in a bit. The other thing that I also wanted to point out is when you're drawing your horizontal and vertical components, notice how the tail of the vertical component starts from the head of the horizontal component. So if you look at this point here, the connection between the vertical and horizontal components is quite important because then that will give you the direction of the vertical and horizontal components. So make sure to connect the tail of the vertical component should be connected to the arrowhead of the horizontal component. All right. Okay, so just to emphasize why we want to break down the diagonal vector into its horizontal and vertical components, we've seen that it's easier to add the vectors when they're all horizontal or when they're all vertical. Yeah, and if they're just in the same horizontal direction or vertical direction, you add them up. If they're in opposite horizontal or opposite vertical directions, you subtract them. All right. Okay, so now let's go to the method or the procedure for breaking down the diagonal vector into its horizontal and vertical components, right? So we again have these two vectors that are diagonal. You look at one vector at a time, okay? It can be overwhelming if you're seeing like a lot of diagonal vectors or a lot of vectors altogether. So look at one vector at a time. Say, let's start with force F1, the vector for force F1. So when we say vector, it's just the arrow that's representing the force, right? So the vector for force F1, it's diagonal, it's at an angle theta1 relative to the horizontal axis. So when you break down this vector, you break down this diagonal vector, you get its horizontal component. Okay, so notice how the horizontal component is drawn. The tails of the tail of the diagonal vector and the horizontal vector meet, right? And then you draw the vertical component. So F1x, x tells you it's the x component. And then you draw the vertical vector, okay, so that the tail meets the head of the horizontal, and you form this right angled triangle. So you should have a 90-degree angle between the components, the x and y components of your vector. So you do the same thing for force 2. If force 2 is directed diagonally downwards, so again, draw the horizontal component. Notice how the tails of these two vectors meet. And then draw the vertical component. Notice how the heads and the tails meet, and again you have this 90-degree angle, right? So once you have the horizontal, once you've broken the vector down, broken the diagonal vector down into horizontal and vertical components, okay, the diagonal vector can now disappear. Right? So yeah, so you can now remove the diagonal vector and you just have the horizontal and vertical components. Okay, you can also remove the diagonal vector for F2, right? And now you just have horizontal vectors and you have vertical vectors. Okay? And it's now easier to add the horizontal vectors together and add because they're in the same direction, and then subtract the vertical vectors because they're in opposite directions. Yeah, so vertical vectors, you have the vertical component for force F1 that's going upwards, okay, and then you have the vertical vector component for force F2 that's going downwards. Okay, they're in opposite directions, so you subtract the two vectors, and then you get the net force along the vertical. Okay. And then for the horizontal vectors, you see they're in the same direction, right? So you have the horizontal component for force F1 and the horizontal component for force F2. They're in the same direction. So you add, oops, about that. So you add the two forces up because they're in the same directions. Okay, right. Is that clear so far? Does that make sense so far? Okay, good. All right, I can see some thumbs up. Right, so the key takeaway here so far is just breaking down the diagonal vector into horizontal and vertical components so that we can get rid of the diagonal vector. Right. So the next question is, how do we get the magnitude of these horizontal and diagonal vectors, right? So, okay, we know we have to get the horizontal and vertical components, but how do we calculate how much is that horizontal and that vertical components. So that's where we use trigonometry in this case, and that's where it's important. That's now why it's important that the vertical, the horizontal, and the diagonal vectors make this right-angled triangle, because any so they form this right-angled triangle. You have this angle between the diagonal vector and the horizontal axis, and you have this 90-degree angle between the vertical and the horizontal components. Right. We can now use trigonometry to calculate for the horizontal and vertical components. So the trigonometry is just a set of rules. So trigonometry says, if you get the sine of the angle theta, so theta is the angle between your diagonal vector and the x-axis. If you get the sine of the angle theta, that's equivalent to getting the side opposite the angle and dividing that with the hypotenuse. So the hypotenuse, if you have a right angled triangle, the hypotenuse is the diagonal. The hypotenuse of a right angled triangle is the diagonal side. The side opposite will be the vertical side, the side that's opposite the angle. And then you have this other side, which we call adjacent side. So the side that's adjacent to the angle theta. Right, so trigonometry says if you get the sine of the angle, that will be equal to the opposite side divided by the hypotenuse of the right angle triangle. And we abbreviate that as SO. Sine is equal to opposite divided by the hypotenuse of the triangle. So if we look at our right angle triangle here, if we get the sine theta, the side opposite is the y component, or the vertical component, right? The side that is opposite this angle theta is the vertical component of our diagonal vector, right? Fy. Divide that by the hypotenuse. So the hypotenuse is the diagonal side of the triangle. So that's the force F. So let's say that's the force F. So let's put some numbers. Okay, let's say, so if we want, we'll put the numbers later on, but now we want to find the vertical component. So Fy, that's the vertical component of your diagonal vector. So if you want to find Fy, so we need to isolate Fy in this equation. So you need to rearrange this equation. Again, you can do the whole building up the equation and then going backwards and undoing the building. But we'll just do the other way, where any number divided by itself is equal to 1. So if you rearrange this equation to isolate Fy is up here, and I want to get rid of F. So if I multiply both sides with F, I have to do on both sides whatever I did on one side. So if I multiply the right side with F, I have F divided by F, that's equal to 1. Then I have to also multiply the left side with F. So I have F times sine theta, so that Fy is equal to F sine theta. So this is the equation for getting the y component, or the vertical component of the diagonal vector. Okay, does that make sense so far? Are we okay with that? How to get the y component? Right. Yeah, a little bit of silence there with no thumbs up, so I'm not quite sure So how do we know F? So F, that is usually given. So this is usually the force. So for example, you have here an object M, and you are pulling on the object with some force F. Okay, so that force is diagonal. So it's at an angle theta relative to the horizontal. So the F is usually given. That's usually what you know. You know the force that is acting on the object, and that force is diagonal. So that is the force F. Given that force F, you want to know what is the horizontal and vertical components of the force F. And that's where you have to use trigonometry, using this equation here to get the vertical component of this diagonal force F. Right? And we did a little bit of manipulation for this equation. So sine theta, this is the basic trigonometric equation that relates this diagonal force and its vertical component, because the side that's opposite the angle turns out to be the vertical component, and the hypotenuse turns out to be the diagonal force. So to get the vertical component, you have your diagonal force F. So this is the diagonal force. You have to multiply the diagonal force with the sine of the angle. So you will be given, if you have a diagonal force, we will also give you the angle theta. So usually you are given F and theta. Okay? We will always give you two things, and we will ask you to find the third thing in the equation, right? Okay, so yeah, this is the equation for finding to find the vertical component is this equation, F diagonal force times the sine of the angle. So let's put some numbers to hopefully that will make it clearer. So let's say you are pulling with a force of 20 newtons. Yeah, so let's say you're pulling with a force of 20 newtons with an angle of 30 degrees from the floor, from the horizontal floor, for example, and you want to find the vertical component. Let me just clear this up. Right, so F, that's the diagonal force. Diagonal force, which is actually given to be 20 newtons, and you multiply that with the sine of the angle. So the Y component for this diagonal 20 Newton force is equal to 10 newtons. Okay. All right, yeah, 10 newtons. Okay, just a warning here, if you're using your calculator and you're not getting 10 newtons, make sure that your calculator is set to be in degrees. So the angle theta should be in degrees. And sometimes some calculators are set in radians. Yeah, so you might want to check the manual for your calculator if you're not getting 10 newtons when you're doing this sine theta, because if your calculator is set in radians, it will give you a different answer. So make sure your calculator is set in degrees. All right, so that's how you get the vertical component. It's 10 newtons. Now to get the horizontal component, there is another basic trigonometric equation that relates the angle to the adjacent side of a right angled triangle. So the basic trigonometric relationship is given here. Cosine theta is equal to the side adjacent to the angle divided by the hypotenuse. Okay, the adjacent side, that's the x component. So this is the adjacent side in your right angled triangle. Okay, so to get the x component of this diagonal vector, you have to use the cosine theta is equal to adjacent side. So if we apply this basic equation to our force triangle, okay, the side adjacent is the x component fx, and the hypotenuse, that's the diagonal force f. Okay. So we do the same thing that we did for the y component. We want to find fx, so we want to isolate. Let me move that up. We want to isolate fx, so we multiply both sides with f, okay, so that f divided by f on the right side is equal to 1, and we're left with just fx on the right side, and then we have f times cosine theta on the left side. Right? So then the x component for your diagonal vector will be the diagonal vector f multiplied by the cosine of the angle. Right? So yeah, for this for our example, say you're pulling at a diagonal force of 20 newtons, so you have 20 newtons multiplied with the cosine of the angle between your diagonal force and the horizontal. So you have 20 multiplied with cosine 30, right? And that will give you an x component of 17 newtons. All right. Okay, are we okay? Are we still okay? Can we still follow? All right, at least one thumbs up, two. Okay, good. All right, good. Okay, so right, a number of thumbs up there, right? So that's how you get the x, how you calculate the x and y components using trigonometry. So yeah, so let's go back now to the procedure. So first we started with a diagonal vector. We have to break that down into its horizontal and vertical components, and then we add up all the horizontal and vertical components. That will give us now a single vertical component, right? So after you've added or subtracted, depending on the directions of the vectors. So for our example here, the two vertical vectors are at opposite directions, so we subtract them. So we end up with a single vertical net force. So this is now the vertical net force. And we do the same thing for the horizontal components. We have two horizontal components in the same direction. We add them up. So we end up with a single horizontal vector that gives us the net force along the horizontal, net force along the x-axis. Okay. So we have these two net forces. To get the overall force, yeah, so here this one, the note here is just this one. So adding the two forces along the horizontal will give us one net force along the horizontal, and adding the two forces along the vertical will give us one net force along the vertical. These are now the components of the net force acting on the object. Okay? If you have a net force along the horizontal, okay, and you have a net force along the vertical. Notice again how the tail of the y component connects with the head of the x component, and then they make an angle of 90 degrees with respect to each other because they are components of the net force. So you have the y component of the net force and the x component of the net force. Right? The diagonal of this right angled triangle will now be the net force or the total force that's acting on the object. All right. Okay, so the question now is, how do we get the net force? So how do we do the reverse of what we did? So what we did, so we have a diagonal force. You broke that down into horizontal and vertical components using trigonometry. Now we want to go the opposite direction. We have the X and Y components. We have the horizontal and vertical components. How do we find the net force, the diagonal vector, diagonal force in this case? We again use trigonometry because we're again forming a right angle triangle here. Just remember that the hypotenuse of the right angle triangle gives you the diagonal net force. Okay? So we want to find the hypotenuse of this right angle triangle that is formed by your horizontal and vertical components. Okay? That is what we want to find, the hypotenuse or the diagonal net force. Okay? Right, we use an identity called Pythagoras theorem. So this is the basic equation that you use. Pythagoras theorem says that if you have a right angle triangle where the vertical and horizontal components make an angle of 90 degrees with each other, then you can calculate this hypotenuse, the diagonal side, by taking the square root of the x component squared plus the y component squared. So this is the x components, the component along the horizontal, and this is the y component, the component along the vertical. So you square the x component, and you know the x component because you've solved the net force along the horizontal. You square that, and then you also square the y component, add them both together, and then get the square root, and that will give you the net force, the hypotenuse or the diagonal vector. All right, and then the direction. So let's put some numbers. So let's say, yeah, we've calculated, let's say earlier, let's say your x component is 17 newtons, and for example, your y component is 10 newtons. How will you get the diagonal force here? You use Pythagoras theorem. Let me just clear this up. Yeah. So Pythagoras theorem says you get the value of the x component, 17, square that, get the y component, which is 10 newtons, square that, add them both together, and then get the square root, and you should get 20 newtons. So if you're having a problem with your calculator, try putting brackets before getting the square root, and you should get 20 newtons for the magnitude or size of the net force. Yeah, so you should get 20 newtons for this diagonal net force. Force is a vector, so you need to get the direction. What is the direction? The direction is given by the angle theta. So this will give you the direction of the diagonal force. How do we get the direction? How do we get the angle theta? It will use again trigonometry. This is the basic equation, trigonometric equation. It says tangent theta is equal to the side opposite the angle divided by the side adjacent the angle. Right? So you can see the side opposite the angle, that's the y component or the vertical, and the side adjacent, that's the horizontal or x component of the vectors. Okay? So in this case, tangent theta is equal to the y component divided by the x component. We want theta. We do not want tangent theta because theta gives you the direction. It's not tangent theta, it's theta, right? So we need to get rid of tangent. We need to do the inverse of the tangent to get rid of tangent theta. And so you have inverse of the tangent times, so this will be a multiplication. Oh, no, it's not a multiplication, sorry. It's just the inverse of the tangent of Fy divided by Fx. So what you do here, so let's put in the numbers. Putting the numbers, let's erase that one. Okay, putting the numbers, find the theta tangent of the y component, which is 10 newtons, divided by the x component, which is 17 newtons. So what you do here is you divide them first, 10 divided by 17, and then you get the tangent of that. And you should get 30 degrees. For the direction. Okay. Are there any questions, or are we okay so far? Can we follow how we can get the so what we did here is when you have the horizontal and vertical components, you can get the diagonal vector by using this Pythagoras theorem, and you can get the direction by getting the inverse tangent of the vertical component divided by the horizontal component. Right? Okay, yeah, we will look at an example later on putting everything together. Now the angle, so let's now focus our attention on the angle because this angle gives us the direction. The convention we'll use, because the angle can be anything if you measure it relative to whatever axis. So for this angle, we should always measure the angle relative to the positive x-axis. So after calculating the angle from this equation, from this trigonometric equation, we have to adjust the angle so that it is measured from the positive x-axis. So say, for example, this is your net force. It's directed upwards and to the right. The angle is measured relative to the positive x-axis, and whatever angle you get from this equation will be your final angle. Okay. If your net force, if this is the net force that you've calculated, is directed upwards and to the left, okay, then the angle that you calculate using the trigonometric equation will actually be this angle, because this will be your x component, and this is the y component for your net force. So the angle that you've calculated using the equation will actually be this angle. It's measured relative to the negative x-axis. So to find the final angle, you have to do 180 degrees minus theta. So a little bit of terminology here. So if this is our coordinates, we know that, yeah, we call this the first quadrant. Quadrant because it's like you've divided the space into 4. So it's a quarter of the space. This is the second quadrant, third quadrant, and fourth quadrant. You have 90-degree angles for every quadrant. Now, if you go around, if you trace a circle going around, okay, going from here to here, this will be 90 degrees. That will be a 90-degree angle. If you go from, so this is positive x, we know that's positive y, that's negative y, and that's so negative x to the left and negative y downwards. So if you go from positive x to positive y, that's a 90-degree angle, right? They're perpendicular. If you go from positive x to negative x, that's a 180-degree angle because you're adding up two 90-degree angles together. And then if you go from the positive x to the negative y, that's a 270-degree angle because you're adding three 90-degree angles together. So you have 90 degrees from positive x to positive y, plus another 90 degrees from positive y to negative x, and 90 degrees from negative x to negative y. So that's a total of 270 degrees altogether if you go from positive x to negative y. And then if you go around, if you complete the circle, going from positive x and going back to positive x, that's a 360 degree angle all around the circle. Okay, and so yeah, going back now to finding the final direction. So if your net force is in the first quadrant, then whatever angle you solve using this equation will be the final answer for your final angle. Okay. If your net force is in the second quadrant, so your net force is in the second quadrant, then your final angle should be 180 degrees minus theta, because then you have, yeah, we know this angle here is 180 degrees, and you want the final angle is measured from the positive x-axis. So you have to subtract from 180 degrees whatever angle you calculated from the trigonometric equation. And if your net force is in the third quadrant, so this is in the third quadrant here, your final direction measured with respect to the positive x-axis will be this angle. And you then have to add 180 degrees because we know from positive x to negative x is 180 degrees angle. So to get the final angle, you should add 180 degrees to whatever angle you calculated from the trigonometric equation. And if your net force is in the fourth quadrant, then yeah, you want to measure this. This is your final angle measured with respect to positive x. So you have to do 360 minus whatever angle you calculated from trigonometry. Or you'll see also you can measure, yeah, this angle here, this direction is also relative to the positive x, but it's in the opposite direction. It's in the clockwise direction. So you can also do a negative angle for your final answer. So it's only when your net force is in the fourth quadrant you can have two answers for your final angle. Either you do 360 degrees minus whatever you calculated from trigonometry, or you do negative of whatever you calculated from trigonometry. All right. Okay, I would say keep this slide handy, because everything will be open books, open notes. So you can always refer to this slide on how to get your final angle. Yeah, just looking at whether your net force is in the first, second, third, or fourth quadrants, and how you get the final angle from these equations below. All right. Yeah, but now I want to go to an example so that we can combine everything together. So say you have an object here and you're pulling in this direction. Let's say that's force A, right? With 44 Newton force, and an angle 28 degrees. And then maybe let's say your friend is pulling in another direction, that's force B, and they are pulling with a magnitude of 26.5 newtons and an angle of 56 degrees relative to the horizontal. And then you have, this is an object of mass M. Anything that has mass will have weight. So let's say you have this weight force, which we call which is called vector C in this drawing. Let's say you have a weight force that's equal to 31 newtons. Weight force or force C. Just to be consistent with this figure here in the slide. So let's say that's the scenario. You have an object of mass M. You're pulling to the right diagonally with a force of 44 newtons. Your friend is pulling to the left diagonally with a force of 26.5 newtons, and you have the weight force that's vertically downwards, 31 newtons. So you have this free body diagram here, and we want to calculate the net force acting on the box. Right, so we have two diagonal vectors and one vertical vector. Again, we look at one vector at a time. So first, let's look at vector A. Okay, vector A is diagonal, so we need to find the components of vector A. Right. We need to find the components of force A or vector A. We've already derived this equation earlier, so we don't need to go through the derivation again. So we know vector A, you can break that down into its horizontal component. Yeah, the horizontal component, notice how the two tails, you start from the tail of the diagonal vector, and you have a vertical component that's perpendicular to your x component there, right? And we want to find this horizontal and vertical components, right? So for the horizontal component, we've seen earlier, we've derived this equation, so we don't have to derive that again. The x component is the side that's adjacent to the angle theta, right? And so we use the cosine function for the trigonometry. And that means we have to calculate, we have to multiply vector A, the diagonal vector. So that's vector A is 44 newtons multiplied with cosine of the angle 28 degrees. So you have the x component, you should get 38.85 newtons. Right? Okay, and then you also calculate the y component. The y component is the side that is opposite the angle theta. Right? So you use the sine theta because y component is opposite the side, the angle theta. So again, have the vector A 44 newtons times the sine of 28 degrees. Then you'll have a y component of 20.66 newtons. Right? Okay, so you've calculated now the x and y components, so horizontal and vertical components of your vector. Finally, check your vectors, the directions of your vectors. So your horizontal component is pointing to the right. And last time we said that if your vector is pointing to the right, that will be a positive. Pointing upwards will be positive, pointing to the left will be negative, pointing that downwards will be negative. So AX is pointing to the right, so that should be positive. AY is pointing upwards, so that should also be positive. So that's the final check that you have to do, is to put the directions of your vertical and horizontal components. Right now, determine the components of vector B. Okay, so vector B will have an x component, bx, and it will also have a y component. Yeah, so forgive my drawing. Should draw that better. By. What happened? Bx and by. Right. So get the components, horizontal and vertical components of your vector B. So bx, so the x component is again the side that's adjacent to the angle. So that will be a cosine theta function. B is 26.5 times the cosine of 56 degrees. You should get 14.82 newtons for your bx. But notice how your bx is pointing to the left. So that should be a negative. Pointing left, because we said that pointing to the left will be negative. Pointing right will be positive. Pointing up will be positive, and pointing down is negative. Then you get also the y components of B. So that will be a sine theta function again, right? So that will be 26.5 newtons for B times sine 56 degrees. And you should get a B of 21.97 newtons, right? The y component is pointing upwards, so that should be a positive y component. Did I write that in? Yeah, this should be the components of force B. Right. So are we okay for the components of force B? Because then I'll erase this, because I actually wrote them for the in the space for my components of C. Right. So that these are the components for force B. Now we now determine the components of force C. Let me just make some space. For the components of force C, notice how force C is directly downwards. So the x component will be 0. There's nothing along the x-axis, and the y component is just 31 newtons. And then it's pointing downwards, so that should be a negative 31 newtons, because you have a downward direction. Right? Okay, and finally, you now have all the x and y components for your vectors. You now add up all the components. Okay, so for the x components, yeah, I put it in a table, so it's easier to see. But these are all the components that we calculated earlier. For the vector A, you have your x and y components. And then for vector B, you have your x and y components again. Notice how the x component is negative, because vector B is pointing to the left. And for your vector C, you only have a negative y component. And then add them all up to get the net force for your vector. Okay. And then once you have your net force along the x and the net force along the y, you can now determine the total net force. So you have an x component x component of 24 newtons. It's pointing to the right because it's positive. And then you have the y component that is 11.6 newtons. It's pointing to the pointing upwards because your total y component is positive. And then the diagonal here will give you the net force for the three vectors. And then you have, of course, the angle there. So using Pythagoras theorem, the net force will now be the square root of the x component squared plus the y component squared. So you'll have the square root of 24 squared plus 11.6 squared. That will give you about 26.7 newtons for the net force. Okay, and for the angle theta, you get the arctangent of the y component divided by the x component. So this was the equation that we derived earlier. So that will be the arctangent of 11.6 newtons divided by 24. So you go 11.6 divided by 24 and then get the arctangent of that. You should have a theta of 25.8 degrees. Okay. Your net force is in the first quadrant. So notice how, so your net force is in the first quadrant. So whatever angle you've calculated using trigonometry will already give you the final angle for the direction. Yeah. All right. Any question about the example? Okay, good. Right, so that's essentially our lesson for today, and you will do a lot of practice in the workshop. So you can proceed to the workshop, look at the workshop problems. It's getting the components, okay, given the diagonal force and some angle, and the angle, you'll get the components, the x and y components of the diagonal forces. And then for the second question, given the x and y components, find the net force, which is the diagonal. And then, given horizontal and vertical vectors, find the net force of that. And then the last question is putting everything together in a worded problem. So, go do the workshop questions, and then let's meet again at maybe 10. Let's see. How much time do you want? Do you want to meet at 10, 30 minutes, 10:40 or 10:30? So how much time do you need? 10:30. Okay, good. All right, let's meet at 10:30 to look at the solutions to the questions. But first attempt the questions and see how you go. I'll stop the recording.